Hello and welcome to YouTube channel Tech Guru Gautam Prasad. This video is on alternators, that is also called synchronous generator or AC generators. So whatever it is said, it is used for the generation of electricity. So let's proceed, my friend, and explore all these three things that is known by the same name. Alternators, synchronous generators or AC generators is the name of same equipment. So, friends, let's proceed. Let's first discuss the learning objectives of an alternator. First, we will discuss the understanding about the operation of a single-phase two-pole AC generator, followed by describing the operation of a simple AC generator. And then we would learn to identify and define the components of a three-phase two-pole AC generator to include rotor, stator, and armature, field winding, slip ring, and brushes. Then we would like to understand the effect of applying DC voltage power supply to the two poles of the rotor, field winding via brushes and slip rings. Then we will proceed to understand that the induced effect that results from rotating the rotor's electromagnetic field past the armatures. So we would keep Faraday's law in view when we will discuss this. Given the armature coil sequence and their physical location, plot the induced AC voltage for the three-phase two-pole AC generator as the function of the time and as phasors. Also, we would like to understand the relationship between the number of poles and RPM of the rotor to induced AC currents frequency. So friends, let's try to understand how electricity is produced. A generator is a machine that converts mechanical energy into electrical energy and helps us in generating electricity. Motors and generators perform exactly the opposite functions. Motor produces mechanical power for us to do certain things, and the generators do the opposite thing. That means it converts mechanical power into electrical power, and that is, transmitted to the places where it will be consumed. However, the motors and generators are essentially the same type of the device, and we will look into that. You can see the windmill has been shown here that has alternators uh, working inside them to produce electricity. Here, there is a small grid that has been shown, and that is purposely that is has the purpose of making it reach to the consumers. And this transmission line is used to transmit power from one place to another, where which basically connects the generating power station to the consumers. And this fan is showing the utilization of the power in terms of getting some useful work done. So it could be anything like you are using induction chulha at your home, you are using ACs, you are using audio system, TV, everything, every appliance that you use at your home is basically based on electricity, and they consume electricity to do certain things for you. Now let's try to understand advantages of AC power. In the case of the motors, AC is something that is natural for the rotary motors. AC causes rotation in the motors in a natural manner. Voltage transformation, AC transformers allow efficient changing of the voltage to enable better power transmission. So, whether it is a matter of transmission or distribution or generation, AC is very natural. And with the help of the transformers, it can be stepped up or stepped down as per the requirements. Power transmission is something that is allowable to hundreds of miles in the case of the AC, but it is limited to approximately 1 mile in the case of the DC. So that DC has limitations of transmissions where AC can be transmitted to hundreds of miles. That is the advantage. So let's try to understand the functioning of the motor, DC motor basically, in order to understand the functioning of the single phase AC generator. So here on the right side, you can see this is the setup of a motor, uh, DC motor basically, having two segments and a single loop coil. Basically, it is fed with DC power, and this conductor carries the current I flowing through it. And because the conductor is carrying current I, is placed in the magnetic field of flux density B, so it is experiencing a force. Left side of the conductor is experiencing force in the upward direction, and the right side of the conductor is experiencing force in the downward direction. These two forces working in opposite direction are called couple of forces, and this couple of force is trying to rotate the conductors in uh, clockwise direction here. And this is the basis of generation of AC power. In fact, if we are not suppose feeding this uh, s- uh, uh, this coil with the DC power, basically we are rotating this conductor with the help of a prime mover, suppose, eliminating the DC power, then what will happen? So if you rotate this conductor in the magnetic field B, then because it is cutting the fluxes according to the Faraday's law of electromagnetic induction, it will induce power. So some voltage will be induced on the left side, some voltage will be induced on the right side of this coil, and they will be additive. So the total amount of the voltage induced will be sum of these two sides voltages. And if you increase the number of turns, this voltage is going to increase with the increasing number of the turns. But let's discuss the shape of the waveform that is getting developed when this coil is being rotated with the help of a prime mover. So here I have tried to show you the phasor diagram and the output waveform of the AC we are getting as the resultant. So if you move this armature with the help of a prime mover in the clockwise or anti-clockwise direction, the EMF is induced in the conductors of the armature, and that reflects between the two terminals of this generator. So basically, it starts working as a generator. So you have to fix up two slip rings instead of these two segments of the commutator. So it starts working as a AC generator. Let's go to the next slide for better understanding of the same thing. Motor to generator, basically rotating DC. So these all these setups are using alternators. This is a car or truck engine that is having alternated as its parts for the charging of the battery that we have in the case of a truck or the car or any other moving vehicle. So this is a turbine. This all is also associated with the generator, AC generator. We have a hydroelectric power station here that uses water power, water pressure to run the turbine, hydroelectric turbine. Next, the basis of single phase AC generator, I was discussing in the uh, previous slides. This turning of this alternator, we are having two slip rings here, and that is connected across a load. So here also AC is generated as I was discussing, and the amount of the voltage induced is EAA, basically between the two slip rings is Vm sine omega t. Omega happens to be the cyclic frequency of rotation of the coil in the magnetic field, and this is the sinusoidal wave that we get in the output, and the phasor and waveform, sinusoidal waveform has been shown here as it is generated. So the three-phase AC generation, idea of three-phase AC generation starts from here. As you can see, this setup is just like the previous setup that we have discussed, but there is an addition here. Instead of having one coil, we have three coils, naming red, blue, and yellow phases. So we have instead of RYB, we have used the terminology A, B, C for the simplicity of understanding here. So we have A dash, B, B dash, and C dash coils. They are 120-degree apart in the on the rotor periphery, and these coils are meant to rotate in anti-clockwise direction, and this will induce EMF separately in all these three windings of the rotor, and the three-phase AC will be generated this way. Three-phase AC waveform will be three different voltages independently, induced in the individual windings. So here you can see we have got three windings ABC, and the voltages induced are sinusoidal in nature, and they have got the waveform like this, and equations of the waveform are like this. EAA dash is Vm sin omega t, EBB dash is Vm sin omega t minus 120 degree, ECC dash is equal to Vm sin omega t plus 120 degree. So that is it. And this rotor is being rotated in the anti-clockwise direction. This is called positive direction of rotation of the electrical machines sometimes. And three-phase AC generator works in this manner. Here the phasor has been shown. These phasors are shown here in the static manner. They are not rotating here, but in fact they are rotating phasors. They keep rotating in the anti-clockwise direction. That is the direction of rotation of the rotor, as shown here. So this is R phasor, this is Y phasor, and this is B phasor. So these three phasors are rotating, but for the simplicity of understanding, this they have been shown static here. So here, if you represent them in the phasor, then EAA dash is Vm by root 2, that is VRMS at an angle 0 degree, and EBB dash is equal to Vm by root 2, that is RMS voltage at an angle minus 120 degree. ECC dash is equal to Vm by root 2 at an angle plus 120 degree. So they are the phasor equations of the three voltages induced in three windings of the alternator or three-phase AC generator. So here also, what is phase sequence? It is important to discuss. Phase sequence is basically the sequence in which the three voltages are achieving their peaks or maximum values. So the phase sequence is the time order in which the voltages pass through their respective maximum values. And the phase sequence is important because this determines the direction of rotation of the connected motors. So whenever you have an alternator, you feed some load with the help of that alternator, and the direction of rotation is determined by the phase sequence of this generated voltages of three phases. So here also this alternator is rotating in anti-clockwise direction, and the phasors are also rotating in anti-clockwise direction. All these three phasors are 120-degree apart from each other. That has been shown. Now let's discuss what is positive phase sequence A, B, C. So A, B, C are the phases here. As you can see, A is here, B is here, and C is here. So if you rotate this rotor in anti-clockwise direction, A will come first to have its peak, then followed by B, and then followed by C. So basically, A, B, C is the phase sequence of this three-phase generated output, and this is the positive phase sequence that we call. So here also A, B, and C, they are rotating in opposite direction. So if you rotate it, you will get A's peak first and then followed by B's and followed by C's. So this phases, this magnitude of the phasor keeps on, changing. So a constant uh, magnitude has been shown in this case, but they keep reducing and then going to its maximum size, and then again the process is repeated in that manner. So rotating vector will be maybe shown in the subsequent slides. Till then, you have to uh, keep on watching the video. Now let's discuss what is negative phase sequence. So the negative phase sequence, if the phases A, C, and B go in this sequence, this is called negative phase sequence, and it is produced when the generator rotates in the clockwise direction. So if you rotate the same rotor in clockwise direction, you will uh, get A's peak first, and then followed by C's, and then B's. So this becomes the new phase sequence, and this is called negative phase sequence. So here it has been shown that how these phases are rotating. So here uh, we are rotating in clockwise direction, and we have the phasors in clockwise direction, rotating in clockwise direction. This is wrongly shown here that it is rotating in positive direction. It is in negative direction, basically. So, what happens in the case of the large size AC generators? Basically, in the large size AC generators, so we have a different kind of the arrangement. So, we have the armature winding, that is three-phase winding on the stator side, and poles are put on the rotor. So why do we do this? Because this has got many advantages. So unlike the generator model that we have just discussed in the last slides with the fixed magnetic field and the rotating armature, it is more practical to have armature winding and the rotate the magnetic field on the larger generator. So rotating armature requires brushes, three brushes for the three phases, and slip rings to conduct the current from the armature to the load. The fixed armature has got the advantage that the generated voltage can be connected directly to the load with no slip rings or brushes. So this avoids the complications due to brushes and slip rings. The voltage applied to the generator generated uh, the voltage applied to the to generate the rotating field is a small DC voltage called the field excitation voltage, and this is a small DC voltage. So insulation requirements are also reduced because of this. So this setup is very much suitable for the AC generation, and we follow this type of the generation. As you can see here, the three-phase winding has been put on the stator, and this rotor having the two poles is rotated with the help of some prime mover, and we get three-phase supply without having any brushes in between. Now let's discuss stator of the generator. The stator is the stationary part in the induction motor. As you must be knowing, the stator winding is placed in the stator slots of the induction motor, and three-phase supply is given to it. In the similar fashion, a stator is slotted in the case of AC generator in the multiple of 6 slots. Three pairs of slots contain identical coils of wires, each with ns turn, and these windings are called armature. So this is the stator of the AC generator, and this is slotted as it is shown here. Uh, this is a stator, and in this slot, a phase coil has been shown. So it's a double layer winding basically. So one part of the conductor is uh, on the bottom side of the slot, and another is on the top side of the slot. So basically, this is a phase of the coil. Similarly, you will have the coils for B phase and C phase in the remaining slots. Other slots have been shown empty. for the simplicity of understanding. Let's proceed. This is the generator rotor, which is fed with DC power supply, or the excitation is given to the uh, rotor poles. So the rotor contains electromagnet called field winding and is connected to the mechanical load through a shaft. The electromagnet is powered by the DC current via slip rings and brushes. So unlike the DC motor application, brushes are not commutating and are not subject to wear. That means less friction is there. So as there is no commutator sort of thing in this AC generator, so you don't have to bother about the frictional forces working on the brushes. They are put on the slip ring, and slip ring is a smooth surface uh, which is not offering much of resistance on the brushes, and that is why wear is not a problem in the case of AC generators. Let's proceed. So here the slip rings that I was talking about is shown here. So as you can see, the brushes are coming out of this is called rocker, and uh, it is brushes are in contact with the slip rings, and this is feeding the pole winding put on the rotor. So allow DC current to flow in the field winding on the rotor to produce the magnetic field. Generator output, the amplitude of the voltage output is a function of the current supplied to the field winding. The stronger is the current of the field winding, the larger the magnetic field, and hence larger the voltage output of the AC generator. So generator frequency, if we talk about what is the frequency of the generator, suppose F is the frequency of the generator of AC voltage. This is the function of the speed of the rotor in RPM. So N is equal to 60 into F. 60 is uh, because F is the number of revolutions per second, that has to be multiplied by 6 to get the RPM, rotations per minute. So the rotor contains multiple number of even poles. It could be 2 pole, 4 pole, 6 pole, etc., or 8 pole or 10 pole. And then omega of the rotor is equal to 2 divided by poles. That means pair of poles, 1 by pair of poles multiplied by 2 pi f radians per second. So n, the speed with which the poles are rotated, is 120 f by p rpm. So here stator and rotor both have been shown. So this is the stator part, and the winding of the stator is here, and this is a 4-pole machine basically, and rotor is rotating in anti-clockwise direction, and here the coils are put on the armature coil is put on the stator, as we have talked earlier. So, what should be the synchronous speed for the AC generators having 2 poles? It is 3000 RPM. For the 4 poles, it is 1500 RPM. For 6 poles, it is 1000 RPM. For 8 poles, it is 750 RPM. And for 10 poles, it is 600 RPM. That means uh, a 2-pole machine has to be rotated at 3000 RPM. Similarly, a 10-pole machine has to be rotated at 600 RPM. So higher the number of the poles, lesser is the RPM required for the generation of 50 Hz of frequency. So that is it. N is 120 F by P is the formula by RPM. So let's talk about an example. Here there is example for 4-pole 60 Hz generator. What is the speed in RPM of the rotor? And second question is that what would be the frequency of 6-pole machine spinning at the same RPM? Means RPM got in the first question is the RPM of the second question, and what will be the uh, frequency in hertz if the number of poles is increased from 4-pole to 6-pole. So basically that is the question. Let's explore. So NP is equal to 120 F by P, number of poles, and this speed is in RPM. So substituting these values, you will get 120 into 60 divided by 4, that is 1800 RPM. You will have to rotate the rotor at 1800 RPM. So for 1800 RPM and 6 pole, the number of the poles, and what will be the uh, frequency basically here. So frequency is F equal to N into number of poles divided by 120. So 1800 RPM multiplied by 6 divided by 120, you get 90 hertz. So 90 hertz will be the frequency for the uh, rotor having 6 poles and rotated at 1800 of RPM. So that is it. The problem is solved. Now let's explore the advantages of rotating machine and a stationary armature type. So high voltage generation is possible with this type of the setup as by increasing the excitation current, you can increase the amplitude of the voltage generated, and high voltage generation is thus possible in this case. And also better insulation requirements, as you are not having any moving part on the armature side, so insulation requirement is less. And also on the pole side, that is the rotor side, insulation requirement is less because the voltage level is less. Excitation voltage is very less and limited to 250 volt DC. Rotor weight is less because only pole winding is there. Uh, if it is a two-pole machine, there will be two windings only, and if it is a four-pole machine, there will be four windings only. So weight is less because for three-phase winding, if we consider on the rotor side, we will have to have three windings at least, and that will create heavier weight. So current collection is easy because a stator side is uh, put on the load, armature is connected with the load, and the current collection is easy. Lesser number of slip rings in the case of rotor because only two slip rings are required for feeding the poles. Alternators are of different types, as you can see here. Gas and steam turbines are there. Gas and steam turbines are there. Diesel generators are there. Hydroelectric power generation is done, and a special type of the applications are there that like nuclear power and alternator windmills. They are all applying alternators to produce AC. Now let's discuss the construction of alternators. So if you look at the construction of the stator, it consists of two parts basically, one a stator and the other rotor. Armature winding is on the stator side, as we have already discussed, and the field poles are put on the rotor. The field windings are excited by DC supply from the exciter and given through exciter is nothing but a small DC generator, shunt generator, and given through the slip rings. So you require a prime mover to rotate the rotor of this AC generator. So exciter, let's discuss what is exciter. As I told you, it is generally a small DC shunt generator or compound generator fitted at one side of the alternator rotating shaft, and it is of low capacity. It is of low capacity with low voltage generating machine having about 250 volt maximum. Its function is to provide electromagnetic field in the alternator for making the generation of AC possible. Now, let's discuss the types of alternators. So, we have salient pole alternator and non-salient pole alternators, or turbo alternators, or they are also called cylindrical rotor alternators. So rotors, if you look at, they are of two types, salient pole type and non-salient pole type, or turbo or cylindrical rotor alternators. So these two types of the rotor have been shown here. As you can see, uh, the rotor poles are protruded and projected towards its periphery of the rotor, and this is called salient pole type of the rotor. Whereas the cylindrical pole rotors are flat, and they are having larger axial length. Axial length of the salient pole type of the rotor is less, but in the case of cylindrical rotor, it is uh, uh, larger as compared to the salient pole type. If you look at the cross-sectional view comes like this, as shown on the figure on the right side. Now let's discuss the salient pole type of the alternator. It consists of cast iron frame which supports the silicon steel laminated armature core. This core is built up of thin sheets basically to take care of eddy current loss. Thinner is the sheet, higher will be the resistance, and this resistance will minimize the eddy current loss in the sheets, and thus it is minimized, and the heating of the core is restricted. Also, these laminated sheets are made of silicon steel to minimize the hysteresis loss. Hysteresis loss occurs where the sheet, these thin sheets have to go through the cyclic variation of the field. The core has slots on its inner periphery for housing conductors. So the core has slots. The stator it is talking about has slots in which the conductors are put as the coils. The silicon steel material reduces the hysteresis loss, and the lamination structure reduces the eddy current loss that I have already discussed, and suitable for low and the medium speed alternators. Example is hydro alternators. So salient pole type alternators are used in hydroelectric generation. So basically, in the hydroelectric generators, the speed is low. That is why salient pole type of the alternator is used. So, what are the advantages of a smooth cylindrical type of the rotor? Let's discuss that. So, this type of the rotor has got less windage loss. So, it is offering less resistance to the wind around the rotor, so less windage loss it has, and not no need of the damper winding as it is required in the case of the salient pole rotors, and good balancing on the of the rotor uh, in this case, as it has got a larger axial length and put on the bearings, so balance is better as compared to salient pole type of the rotors. Soundless running. So this type of cylindrical pole rotor is soundless in nature. Good cooling to the field because it is distributed one. So distributed on the periphery of the rotor, uh, this winding, DC winding on the rotor. So cooling is better as compared to the salient pole of the rotor. Hunting is a problem in the case of AC generators or synchronous generators. Due to inertia of the rotor, it cannot achieve its final position instantly if load variation on the AC generator takes place. That means if the connected load varies quickly, then uh, hunting is produced in the AC generators, and that has to be taken care of. While achieving the new position, due to inertia, it passes beyond its final position corresponding to the new load, and oscillation starts. That is basically called hunting. and this will produce more torque. This will try to reduce the load angle, and load angle is the angle between the stator and the rotor poles. Basically, they fall apart because of the variation in the load, and the rotor saving in other direction, swing in the other direction. So it starts swinging in other direction when hunting occurs. So there is a periodic swinging of the rotor on both the sides of the new equilibrium position corresponding to the load, and such swing is called hunting. So this oscillation swing is called hunting. So the causes of hunting, if we discuss, main cause is sudden change in the load, and it could be a fault condition in the system. Sudden change in the field current can also cause hunting. Cyclic variation of the load torque is another cause of the hunting. Now, how to reduce the hunting? So you need damper winding to reduce the hunting effect, and rotor oscillations due to the fluctuation of the load. And you can also use flywheel, that's a very heavy wheel, to take care of hunting. So increase this flywheel increases the inertia of the prime mover and maintains the rotary speed constant. So basically, when it the speed tries to go down, this flywheel compels the rotor to rotate at the same speed because of its inertia. So happens in the case of a speed reduction, that is also resisted by the flywheel. Effect of the hunting. So the causes of variation of the voltage supply, because of hunting, variation in the supply voltage also occurs, increases the chance of losing synchronism. Because of hunting, loss of synchronism could also happen. Increases the possibility of resonance. Resonance is the condition when natural frequency of the uh, material with which the rotor or a stator or the whole machine is made matches with the frequency of oscillation in the case of the hunting. So that's a very devastating condition. It can, break the foundation bolts if the resonant amplitude is very high. So huge mechanical stress may be developed because of this. Machine loss increases, and temperature of the machine rises. Now let's discuss damper winding. So in the pole face of the salient pole rotors, small holes are provided on the pole tip, and copper bars are inserted in these slots. So the end of all the bars on both the sides are short circuited by the copper rings to make closed circuit, so that current flows in the closed circuit. This winding is called damper winding. As you can see in the picture, uh, uh, this is the damper winding. Bars are inserted on the pole tip slots, and they are sorted on either side, this side and opposite side of the pole also. So it takes care of the variation in the load that causes hunting. Advantages of the smooth cylindrical type rotor. So, a smooth cylindrical type rotor, as we have already discussed, that it causes less windage loss, no need of the damper winding in this case, good balancing of the rotor, soundless running, and good cooling of the field because it is a distributed one. Now, let's compare the salient pole rotor and the cylindrical pole type of the rotor. The first point of difference is the salient pole rotor has got larger diameter, and cylindrical pole rotor has got a smaller diameter. So if you will see diameter wise, salient pole rotor has got a larger diameter, and cylindrical pole rotor has got a smaller diameter. Salient pole has got a shorter axial length, but cylindrical pole has got longer axial length. And salient pole rotor has poles projected towards its periphery, and in the cylindrical pole rotor, no projection as such is there. They are a smooth cylindrical one. There is no need of damper winding in the case of cylindrical rotor, but we need damper winding in the case of salient pole rotor in order to stop hunting. Uh, Salient pole rotor is suitable for low-speed hydro generators, and cylindrical pole rotors are suitable for high-speed turbo generators, where the RPM could be 3000 RPM, but here it could be 600 RPM, as low as 600 RPM. So windage loss is higher in the case of salient pole rotors, and windage loss is very less in the case of cylindrical rotors. So they are the points of difference, my friend. Let's proceed. Speed and frequency, they are related as F equal to Pn by 120 that we have already discussed. These are the different types of the slots that are used in the case of AC generators. One is called open type, semi-closed type, and this one is closed type. So there are different types of the slots in which winding is put, basically wide open, semi-closed. Now let's explore the terms used in the armature winding. You have conductors, you have intern, you have turn, you have coil, you have pole pitch. Pole pitch is nothing but the number of slots per pole. Coil pitch you have, this is distance between the two sides of the coil in terms of number of slots. Slot angle is basically the angle made by one slot at the center. This is 180-degree divided by number of slots. So, different types of windings have been discussed in this slide. AC winding is of two types: three-phase AC winding and single-phase AC winding. And now, single-phase, three-phase AC winding is of two types: single layer and double layer. So, single layer could be of mush type, concentric type, and concentric type could be unbifurcated or bifurcated. A double layer type could be lap winding or wave winding, and this lap winding or wave winding is again subdivided into two parts: integral slot winding and fractional slot winding. So integral slot winding and fractional slot winding, they are again subdivided into two parts: full pitch winding and short pitch winding. So we will see all this in the subsequent discussion. So friends, thank you very much. If you like the video, don't forget to give a thumbs up. If you want to ask any question, you can write in the comment section. I would like to reply it as early as possible. Uh, if you really liked it and you find it applicable, useful for some of your friends, do share it with your friends in the group on the Facebook if you like. And if you are not subscribed to the channel yet, I would suggest you to subscribe to the channel for getting the updates about the new videos. Thank you so much.